Okay. Okay. So yeah. Thank you. Hello everyone. My name is Samuel, and I'm a graduate from Binus University. First of all, I would like to thank to the IC for the opportunity that has been given to me, so I can present out. Oh yeah. So I can present about my thesis today. So the title of my thesis is Behavior Analysis of Irregular Structures on Sloping Ground using Response Spectrum and Pushover method. So the background of why I choose this research is, as we know, Indonesia is located in the Ring of Fire, which means Indonesia will have a lot of hills and mountain topographic. So it is very possible that in Indonesia, we build like village or even a high-rise building in a sloping ground. For example, in the picture shown in the left side, there are villages somewhere in Magelang that built on sloping ground. I also give an example in the right picture for high-rise building that being built on sloping ground. Also, because Indonesia is located in the Ring of Fire, it means that Indonesia will experience a lot of earthquake. And because of this, I want to do more deeper research about the behavior of structure, especially in sloping ground, to resist or when a seismic event happen. So the research that I do is using nonlinear analysis. So nonlinear analysis is a study of how structure behave under load beyond the limit of linear assumption. One of the nonlinear analysis method is Pushover method. So a short story about Pushover method. It was first introduced in 1996 in ATC40 document. And then it kept being developed over years until now. It like in document FEMA 356, FEMA 440, and ASCE 41 2017. The result of nonlinear analysis is building performance. So building performance is being categorized in four. There are four conditions: operational, immediate occupancy, life safety, and near collapse. So operational is where the building, after a seismic event happen, and the building still can be operational fully without having any problem. For immediate occupancy, the building it is safe to occupy after unseismic event happen, but have minor damage. In life safety condition, the building is also for people are safe to evacuate, but the building suffer significant damage. For near collapse building, the building is also safe for people to evacuate, but we cannot use the building anymore because it is too dangerous. And then move to my research model. So in my thesis, I use three research model. So the first model is regular building on flat ground, and the second model is irregular building on a 5-degree sloping ground, and the C or the third model is irregular building on a 10-degree sloping ground. So before jump to the result of my thesis, first of all, I would like to explain deeper about my model. So as you can see in the left picture, the sloping ground location is located in the back of the building. So on the sloping ground is only happen in the y direction. Also, you can see in the plan view on the right side, the two row of the column in the back will be more shorter than the column in the front. Also, this is the clearer picture of my building from, if you can see from the X direction. So in the two column in the back is shorter than all of the column in the front. So the result of my model, first of all, I compare the linear result, and then later I compare the nonlinear result. For the linear result, I compare first natural period. You can see in the top left chart, the natural period will be more shorter when there are sloping ground occur. Why? It is because the stiffness of the building that being built on sloping ground will increase. As you can see in the chart on the top right, the building B increased 10% in the stiffness. The building C increased 45% in the stiffness. So if you based on the formula of period, the T formula, the bigger and the higher the stiffness, the smaller the period. And then the second thing that I compare is base shear. So in the base shear from my model will be more lower when there is sloping ground occur. Why? Because when there is sloping ground, the building will have less mass for seismic mass. And also, in my thesis case, the calculation for seismic response coefficient is using Tmax. So the fundamental period of the building is not affecting the base shear. And then the last result for my linear result is drift comparison. So for the drift comparison, you can see on the graphic in the top left, it is for X direction. For the X direction, my building will the drift will increase when there is the building is being built on the sloping ground. As you can see, the model A, B to C significantly the drift is significantly increased. Even my model C is crossing the drift limit for that being written in the code. Why? It is because when there is sloping ground, the building have torsional irregularity. So you can see in the table that in the right side, for my model B, in story 1, it have torsional irregularity. And my model C, it have extreme torsional irregularity. But in the Y direction, where the sloping ground occur, the drift doesn't change much or relatively the same. And then the last result is my nonlinear result. Nonlinear results, the result is in performance level. So you can see in the left top, the performance level in the X direction will decrease. Where you can see in my A model or building that being built on flat ground have performance level in immediate occupancy. But for my model B and C that being built on sloping ground have performance level in life safety. But for the Y direction, the building performance doesn't change much, which is all the model in between immediate occupancy and life safety. Also, in my research, the building is being function as apartment building, and it is comply the requirement, which is in group 2. And I use decent earthquake, so my building will be in between immediate occupancy and life safety performance level. Okay, and the conclusion of my thesis is 1, the steeper the slope of the ground, the shorter the natural period, and the lower the base shear force. Second, for building on sloping ground, the drift increase in the X direction. The X direction is the direction where the column on the left and the right side of the building have different height. However, in the Y direction, where the sloping ground occur, the drift relatively unchanged. And then the third, the performance level of a building on sloping ground decrease in the X direction, while in the Y direction, the performance level remain relatively the same. And then the last one is suggestion for the next research. First, for the future research can be done using nonlinear time history analysis because it can be used to observe the building respond to earthquake in more detail. And then second, future research can also pay more attention to the condition of the building plastic hinge when assessing performance level to identify critical point when the building is subjected to an earthquake. Yeah, that's all from me. Thank you.
Thank you very much, Samuel. That was a short introduction to, I'm sure, what has been a long research project for you. So does anyone have any questions on that?
Thanks, Bob School is my name. A very good presentation. Thanks very much indeed, and very interesting. The thing that is obvious that in the X direction along the slope, the conditions change significantly as the slope increases. And the Y direction, they seem to remain fairly stable. Taking your work a little bit further, what is the necessary corrective factors that need to be done in the X direction to try and maintain similar stability in the X and Y direction? Is that possible for you to, I know you haven't done it yet, but is it possible to go to that next step and looking what improvement can be made in the X direction to give similar results, X and Y direction? Thank you.
Okay, I will answer the question. Yeah, I don't do that, but as I know, you can improve it by give on the other side more stiffner, more stiff element. Like you can increase the dimension of the column, or you can increase the dimension of the beam on the other side, not in the sloping ground, but in the opposite direction. So you will have a relatively stiffness in the right and the left side same. So you don't suffer torsional irregularity.
Oh, okay.
So I'm reading online question from Michelle Angela. How to interpret coefficients in a linear regression model?
Sorry, but I don't really understand the question. Can you explain it more to me? What coefficient of
While we see if there's anything else on that. Are there any other questions? Preferably clear. Don't think we're going to get. It's obviously very important in Indonesia. Over the years, we've had a number of talks about earthquakes, and of course, tonight's topic is also earthquakes. There's no escaping them. They happen. And the research that you've done is certainly helping people to understand what precautions they can take to try and make their buildings more resistant to earthquake. And certainly that's ultimately going to save people's lives. So I think it was a very interesting and useful research topic, and I thank you for sharing it with us. Thank you.
Thank you.
So we have that's Samuel who's given our first presentation, a supporting speaker. We have two main speakers tonight, Glyn Addicott and David Meigh. Those of you who have a longer memory will know that Glyn Addicott has addressed us before on the topic of exploding pipelines, particularly pipelines suffering from surge and other issues. I think that was about 5 years ago. So we welcome him back, and he's for those of you that don't know him, which is probably most people, he's got a long experience on the hydraulic design of pipelines, claiming to have worked on 300 different pipelines around the world. And he's a director of a company that specializes in pipeline projects and looking for solutions to the problems that we get with pipelines. He's going to speak on the Palu earthquake reconstruction and what's been done since it happened to build back, hopefully, more resistant infrastructure to any future earthquakes in Palu. And our second main speaker is David Meigh, who's the ICE Indonesia representative. David's been in Indonesia longer than most of our students here. He's got more experience than any of us on working in Indonesia on water resources and irrigation. He has also worked on the reconstruction in Palu, and he's going to share that experience as well. So I think that's all I need to say. David is going to introduce the subject to you because he's got the background knowledge on the earthquake in a way that, it's already 6 years since the earthquake in Palu. Some of our students here are probably unaware of it because they would have been playing with their toys still at that time. So David will tell us a bit about the background, the earthquake that happened, and what made it so damaging. And he will then hand over to Glyn to make the first presentation. We think we'll slip in some questions after the first presentation, and then go on to David's own presentation. Glyn is joining us online, and David is here in the EP with me. So without more ado, I'll hand over to David to introduce the Palu earthquake. Thank you. Oh, that was okay. Yeah, that was correct. Yeah, that's correct. Good evening, ladies and gentlemen. I hope we're going to give you an interesting presentation. Some of you may remember that about 5 years ago, we gave a triple presentation on the earthquake in Palu that happened in 2018. Since that time, some of us have been engaged in repairing the damage that was done. I personally was engaged by the Asian Development Bank as an engineer to first of all look at and provide any advice on the designs, and secondly, I was sent out there twice to look at the construction and give some advice on the construction. Glyn similarly was appointed by ADB to first of all give advice on the design, and secondly he had a trip out there to look at the construction. The earthquake happened on September the 28th in 2018, and it was 7.5 magnitude earthquake. So, somewhat to the north of, if you look at the left-hand map, it was somewhat to the north of Palu itself, but it was along the line of a fault. Well, I hope no one minds if I say Indonesia has plenty of faults. But this one extended right through the center of Palu and right down the Palu Valley. And you can see from the first map that there's a whole series of shakings, very severe shaking in the whole of the valley. This has been somewhat ignored by the designers, but when you looked at the history of earthquakes, you can see that there's a whole series just to the east of the fault. And then this last map that comes up, you can see that these are the areas that shown of liquefaction, and one particular village called Pushover got the full brunt of it. There is a video showing this, but I wasn't able to find it, but never mind. This shows the village of Pushover before the earthquake, and you can see that many, particularly to the right. Oh, sorry. Why am I not seeing this on the screen? Oh, okay. You can see to the right, there's many rice fields that the farmers here were pouring water on what are very sandy soils, very unstable soils, particularly when the water table comes up. It makes them very, very, very insecure. And these are actually on quite a steep slope. It's a 5% slope. So keeping your eye on photograph. And this not only happened in Pushover, it happened in 3 other places as well. And altogether, I think it killed something like well over 2,000 people. Altogether, there were something like 3,600 people killed in this disaster. So, what was the result? Well, actually, many agencies stepped up to the mark and provided assistance, as well as the Asian Development Bank. There was the World Bank, that was JICA, the Japanese aid agency. There was UNDP, and many more stepped up. Now, the Asian Development Bank took on 4 main projects, and if you can see from the map, you can see the Gumbasa irrigation project. This is to the south of Palu. Palu is the grey area near the coast. And then
just to the south of it, you can see the Pasagala pipeline intake, and you can see the blue dashes are the alignment of the pipeline, which very closely follows just above the main canal of the irrigation works. But that wasn't the only water supply project. The ADB also looked at the Paneki water supply and helped to repair that. And there was a new pipeline just to the west called the Dayu, which used a sediment weir. And then to the north of that was the Tondo pipeline. So there were 4 pipelines that ADB was involved in improving. There was also the fishermen's harbors. There were 4 fishermen's harbors. Many of the earthquake caused a tsunami that damaged many of the fishing boats because they were exposed in the bay. So they requested some protection for their fishing boats. So there were 4 fishermen's harbors produced. I had inputs in the intakes of the water supply treatment works, and I had intake on the fishermen's harbors. I also helped with the specification of a valley groundwater monitoring scheme to try and monitor any further risks of liquefaction. But that was eventually taken over by JICA, the Japanese agency. So we won't talk any further. So basically, that's my introduction, and I hope to hand over to Glyn.
Thanks, David. Yeah, hopefully you can all hear me okay. I can't share my video from my screen, so I am here in face, so it's not letting me. I don't have permission, but I'm happy to proceed with just the slideshow. So first of all, can I check? Can everyone hear me okay?
Yeah, we can hear. Yeah, we can hear you okay, Glyn. Don't worry.
Excellent. Right. Okay. I will share my screen then. So hopefully this is the bit that I was worried about. So hopefully you can also see my screen, which will be great.
Yeah, we're okay. We got it.
Yeah, brilliant. Okay, so I'll just show the slideshow. Okay, so first of all, I apologise for not being there in person. I would have liked to have come out, but commitments elsewhere are preventing me. But I will be in Indonesia next month. It's my favourite country, and I love coming out. So it's always a fantastic experience. But hopefully I can share some of the insights into the work that I did in my company. So first of all, my company are based in near Cilandak in the Alamanda building, so PT hydraulic analysis in Indonesia, and we were asked to support the ADB in a number of areas following the Palu earthquake. So first of all, they asked us to carry out a design review of the new Pasagala raw water pipeline that was to replace the pipeline that failed in the earthquake. Similarly, to carry out a design review of the new water distribution network and the supply to the villages and houses in the area. And then two new other areas. Once the raw water pipeline had been built, they asked me to fly out to the region and just inspect the pipeline and make sure that it had been constructed correctly, and it had indeed been built back better, which is definitely the phrase that was used a lot. And then on the back of that, which is probably kind of the most interesting bit, I was asked to support the ADB with actually writing national guidelines for the design of disaster resilient water supply systems in Indonesia based upon international best practice. And on the back of that, really what struck me as being sort of quite unique with Indonesia was the fact that if you look at all the other countries that are in earthquake prone countries, so the likes of the United States, New Zealand, Chile, Japan, which are all on this ring of fire, as it's called, which Indonesia is also installed on the plates. Actually, Indonesia is quite unique in the challenges it faced due to, as David mentioned, is liquefaction, and that's where basically the whole area just turns to a very, very unsupported soil. Water comes in and the whole ground moves and moves in some cases several hundred meters. So it's fairly devastating. And most of these other countries on the Ring of Fire don't suffer from liquefaction to anywhere near Indonesia does. And therefore that presents some challenges, because any guidelines or best practice used in these other countries don't really apply directly to Indonesia in certain areas. And that's why I was asked to support with guidelines. So the best way to explain this is, and I know it's quite hard to see, but if you look at the picture on the bottom right with the red circle on, you can see that I'm not actually circling a cow here. It's actually, you can see grass, you can see green fields in this, and they were trees. So that whole land there, as you know, was fully covered in trees, as the surrounding land is either side of the picture. But liquefaction, you know, basically just moved all the trees, and therefore it became open land. And therefore any pipes that are laid in these areas, you know, are very prone to failure, because as the ground moves, the soil moves, so does the pipeline. And you can see that from the picture at the top. In this case, the pipe, the original pipeline was installed on above ground supports, and because the supports moved, the pipe moved and failed in multiple locations. And this earthquake in 2018 caused very, very significant damage to the water infrastructure. And certainly liquefaction is the main concern when building back better. And I spent a lot of time looking at ways to better build pipelines to survive liquefaction. But ultimately, you know, there comes a point when the liquefaction is so serious and so severe that it doesn't matter how much money you spend on a pipeline. Ultimately, it probably is going to fail due to liquefaction. And therefore, you have to focus on the cost risk benefits and look at maybe actually accepting the pipe's going to fail, but putting in practices to ensure it can be repaired very quickly. First of all, by knowing where it's failed, but also by having the spare tools, pipes, and materials to actually make repairs. So therefore, for severe liquefaction events like we had in Palu, we should actually move folks away from a costly design and actually just look at ways to repair the pipeline quickly and safely. So to give you an idea of what other countries would do in this area, so the picture on the left, figure 1, is it's called earthquake resistant ductile iron pipe, or ERDIP, and it's a special pipe designed and used extensively in Japan. So following some significant and severe earthquakes in Japan in the 1960s, they replaced all of their water network pipe with ERDIP. And very simply, what it is it's socket joined lengths of ductile iron pipe that first of all can fully rotate, so they can fully twist in the joint, so they can rotate through 360 degrees. But also they're each allowed to move to up to 5% of their length. So as the pipe forces of the earthquake applied, the pipe's sockets can move in and move out from each other depending on what's happening, up to 5%. Once the pipe moves out by more than 3%, it basically locks in place. So each pipe section is effectively allowed to increase in length by 3%. And if you imagine that on a network, suddenly actually you can accommodate several hundred meters of movement of the pipes through using an ERDIP. But the problem is it's very expensive and it's costly. Other things you can do, you can put in flexible joints. So the picture on the right would show how flexible joints can be installed. So if you're on a fault, actually all the pipe sections are allowed to move. And I'll cover this in more detail in a minute. Now, if you want to go to real extremes, you can look what they do in Alaska in the United States. So Alaska has got a lot of issues with earthquakes, and there's a lot of oil and gas pipelines that are stalled across Alaska. And this one is an example. If you have billions and billions of rupee, you can actually design your pipelines to withstand earthquakes. And how this works is you can see that the pipeline is actually installed on Teflon sliders. And that allows the pipeline to move in multiple different directions and to slide effortlessly and frictionlessly on these supports. So it's a very significant ground movement or liquefaction event would allow the pipeline to survive. But it's simply not cost effective to do. Obviously, oil and gas industry has a lot more money, and the product is a lot more valuable. So it's worth keeping in the pipeline. So what we did on the Pascagoula pipeline was we found a number of flexible joints. So firstly, the main conclusion that I came to with this pipeline when it comes to design was that it's perfectly acceptable to use galvanized iron pipe, which is very common in Indonesia and cheap to manufacture for above ground sections in low risk earthquake areas. And that's basically traditional pipes on support above ground. But where there is a risk of liquefaction, it's better to actually put the pipes below ground and use high density polyethylene. And that allows the pipeline to move more freely below ground, but it moves less than it would if it was above ground, because the soil provides some resistance. But you still need to allow for movement where your above ground pipe, your GIP pipe, connects to HDPE. And in this case, we use these flexible couplings, and you can actually see on the right that there's these bolts, and these are what are called sacrificial bolts. So these are designed to snap and break if there's liquefaction and the HDPE pipe starts to move. And then you have rubber bellows that can then expand and adjust to try and withstand as much of the movement due to liquefaction. So there's a number of these placed where we go from above ground to below ground pipe work. Fault crossings, though, are a real challenge. So we've covered liquefaction, but where the pipeline actually passes a fault crossing, you can have one half of the pipeline moving considerably and the other half not moving at all, or they can both move in different directions as the two faults and plates rub together. So where you pass over a fault line, you look to actually have a dog leg structure. So you have a structure that the pipeline bends, and you change the pipe route with a high radius bend, so a very swept bend. And that does allow the pipe to move and adjust slightly without failing. You also look to use a thicker pipe wall, so a much stronger pipe at fault crossings and for high quality welds to minimize the risk of failure. And there, when you actually cross the fault, you look to have the pipe moving angle of between 90 and 100 degrees to reduce pipe strain. So you wouldn't do necessarily a straight across the fault. You move it at an angle. And you try and avoid sharp directions on the approach to the fault. So whilst you have a bend on the actual fault itself, coming up to the fault, you try and have a straight section. And also you minimize the pipeline depth as well. If the pipe is buried deep at a fault, then it's more likely to fail. So you have a very shallow pipe, and that minimizes soil pipe friction. But what we did on the Palu pipeline, or we tried to do, was actually develop a quite a novel approach where we actually install the HDPE pipeline and liquefaction areas in a concrete culvert. So you have a concrete culvert, and that concrete culvert is filled with a very light pumice stone or geofoam. So a stone that can crush and move and adjust and compress. And what that does is it allows the pipeline to move within the culvert, but not too much that it will fail. So it's allowing some movement due to liquefaction, but minimizing it. And that backfill takes a lot of the energy out of the earthquake, a lot of the force, and that will minimize the risk of pipe failure. Ultimately, if your pipe's going to move up to 400 meters, as we had in that earthquake in 2018, failure is inevitable. But this is the best that you can do for a relatively low cost solution. And we use HDPE because it's flexible and it responds well under strain, unlike metal pipe. And it's just the only thing there's a risk with HDPE pipe is if there's a lot of friction from the soil pipe rubbing together. So you try and minimize that by using a light backfill. And this basically it eliminates the pipe soil friction issues, and it does permit sideways movement of the pipe. So it's the best you can do effectively without spending too much money, and that was our preferred solution. So these were our design recommendations. Now, one of the key issues you've got with HDPE, which I stress time and time again when I speak to pipeline engineers, is that it's prone to ultraviolet light. So as long as that pipe is exposed to sunlight, and obviously there's a lot of sunlight in Indonesia, there's a lot of UV light, it will weaken it, and actually it reduces the pressure rating of the pipe. So temperature and sunlight are a big issue on HDPE. So both UV light from the sun, but also the temperature of the fluid. You can see here if your water is warm. So say your water in the pipeline is at 30 degrees, you actually have to reduce the pressure rating of your pipeline, depending upon the type of HDPE, by potentially as much as 35%. So I was slightly concerned when I did the construction review on this pipeline to see at this point that the pipeline hadn't been buried and it was actually left in the sun, and that in itself will weaken the pipeline over time. So if you ever, as a civil engineer, pipeline engineer, use HDPE pipe, it's really important that you keep it in a warehouse that has a roof on it, so it's not exposed to UV light in the yard. But also when it's laid and installed, you cover it as quickly as possible, and also be careful with damaging it as well. And you can see here the picture on the left that one of the pipe sections had been damaged, possibly by some sort of vehicle hitting it. So again, it's quite susceptible to failure. So it's great product in terms of it bends and it can strain. Can withstand a lot of strain and stress. It's extensible. It's quite flexible, but you need to be careful with temperature and UV light. Now, the next point to note as well that was spotted on the construction view, because this pipeline was built and then left empty, so completely full of air for several months as the construction went along. Because of the temperatures in Indonesia, that there was thermal expansion in the pipe, and you can see here examples where the pipe was painted, rubbed off on the right due just simply to the sunlight flaking the paint off. But also where it's been on these supports, you can see that actually the pipe has been moving in these supports, and in some cases the rubber's been pulled away. So really we should have had expansion joints on the pipeline. An example of expansion joint, for those that don't know, which they're very common in the Middle East, is basically a U section that allows the pipe to expand in either direction, the X-plane, to mean that you don't have these issues. So what I was asked to do was come up with an ideal pipe material for earthquake, for installing pipelines in earthquake regions. And the two main, almost common products that are used in Indonesia are, as I said, galvanized iron and HDPE. And I produced this design matrix to show the pros and the strengths and weaknesses of the two different pipe materials. So, for example, galvanized iron has good tensile strength. HDPE is elastic and stretches more. It's easier to install the galvanized iron pipe. It can withstand UV. It's easy to maintain. It's easy to repair, but it doesn't last as long. It is more prone to failure. It's not suitable for liquefaction areas, and it can't withstand corrosion. And also it has a relatively high internal roughness. So generally speaking, you get less flow rate delivered through a galvanized iron pipeline because of the friction losses. But it's suitable for fault crossings, and it is cheaper. HDPE pipeline is obviously, as I mentioned, it can withstand corrosion. It's more distensible and it lasts longer. So there's pros and cons. But if you actually then try and combine the two pipe materials, as we did in the Palu pipeline, then actually you get a really good fit for your solution, because you take the strengths and advantages of those pipe materials in their own areas, and it allows you to produce a robust design. So we used a combination of galvanized iron above ground and HDPE below ground, and that fitted the best. That's the best possible criteria for pipe selection you could have, given your cost constraints. I'll come to pipeline management systems shortly. So design matrix, there's 5 key points for designing a pipeline in an earthquake region. So first of all, planning. So look at the history of earthquakes in the region, look at the severity, the liquefaction, look at, understand whether you've got problems and issues, and then what your design needs to do to maximize the chance of survival in an earthquake. Then look at pipe material selection. I've already mentioned this, that there's pros and cons, strengths and weaknesses of different materials. So look at your pipe material and think, what's the best material? Probably the obvious one is the pipeline route. I mean, if the pipeline passes through a liquefaction area, first of all, do you have to go through that area? Can you bypass it? But if you can't, then look at the depth of liquefaction. And then you could potentially, if you can directionally drill your pipeline several meters below ground underneath the liquefaction areas, then you have a chance of surviving the earthquake, or a better chance of surviving the earthquake. So pipe routes, really important. Where you are in a liquefaction area, if there is a high groundwater level, you consider lowering the water level by actually using that water for irrigation. So actually put in wells and keep the water table low and keep the pipe above the water table. So therefore liquefaction won't occur if there's an earthquake. And that's an added bonus if you then use water for irrigation. So you have, minimize risk of failure in an earthquake, but also you have water available for irrigation. But ultimately, and where we really are with the Palu pipeline, is do the best you can with the design, but ultimately prepare for it, accept that if there's another earthquake as severe as 2018, it probably is going to fail. So then you want to be able to detect where it fails very quickly and respond to that. And that's as important as anything. So it's having the spare parts, the tools and the procedures, access roads to be able to get to the pipeline, to repair it, ideally within 24, 36 hours of a failure, to maintain water supply to the region. And therefore pipeline management and advanced leak detection systems are vital, so you can detect where the leaks are. And this is one of the first advanced leak detection systems put on a water pipeline in the region. So the Palu pipeline has a very advanced hydraulic pipeline leak detection system on. So if you imagine this is your pipeline, or a section of pipeline, and effectively we've installed pressure transducers in blue at various points on the pipeline. So approximately every 5 kilometers, there's a pressure transducer which is powered by solar that transmits via a mobile phone chip the pressure reading from the pipeline. At each end of the pipeline in red, we have a flow meter. So we measure the flow going in, we measure the flow going out, and we measure the pressures along the pipeline. And therefore, when there's no leak, obviously the flow going in is the same as the flow going out, and your pressure loss, or your hydraulic gradient, is fairly constant along the pipeline because there's no leaks. Then you have your earthquake. And you might have pressure and flow control in your pipeline as well, which is fine, and the leak detection system can account for that. But then you have your earthquake and your leak. So you have a leak, and what that does first of all is it causes the flow to change. You have a flow change that travels away from the leak, and also a pressure change. So flows and pressures change, and they travel along the pipeline. As they travel on the pipeline, depending how close they are to the different pressure sensors, or how close the leak is, the pressure sensors see that change in pressure at different times, and eventually it will work its way all the way back to the start end of the pipeline, and your pressures and flows will change. But the hydraulic system that's monitoring the pipeline will then suddenly see these changes in pressure. So the pressure at the start of the pipeline will fall, and the flows will increase as you're feeding more flow into the pipeline. So flow in versus flow out, that's a good indication you've got a leak. If more flow's going in than's coming out, you've got a leak. But then you can use your pressure sensors and your hydraulic gradients to automatically calculate where the leak is. And that will then give you a leak location, generally to within 40 or 50 meters of the actual location. And it will normally tell you that within a few minutes. So within a few minutes of the earthquake happening and the pipe failing, the leak detection system will tell you that you have a leak. It will tell you how big the leak is. And more importantly, it will tell you where that leak is, and you can then repair it. So what do the pressure sensors look like? Well, this is what example one here. So you can see in this case that the transmitter is in a cage. You have the solar panel that powers it, and that's actually the pressure transducer in red circled there. So it's a simple, low cost, basic SCADA system. So it's this basic supervisory control and data acquisition system that transmits the data via phone, cell chips into the control center, and then detects leaks. So it's a very low cost and effective way of monitoring the pipeline for leaks. So just to cover last point really. So one of the other exciting things I did on this visit I had to site was walk the route of the Tondu pipeline. So I've focused on the Pasagala pipeline, that is the main water supply pipeline in Palu, but also there's a second pipeline that's being constructed from Tondu, and for that I had a very exciting journey into the jungles of Sulawesi. It was just unbelievable. You can see on the picture on the right, there's you can maybe make out there's a digger, and that's because there'd been a landslide and we had to stop the truck, and the digger had to clear the way for us to get to the intake works. So I walked through some of the most beautiful jungle and scenery I've ever seen in my life. And that's saying something. For those of you who know the UK, I live in an area called the Lake District, which is an area of amazing natural beauty. But honestly, this was something special in Tondu. It was something I will never forget. It was an experience, but also highlighted the challenges of laying pipelines in Indonesia, because the terrain and the issues with the gradients of the pipeline are unbelievable. And it really gave me a insight into actually how talented construction engineers and construction workers are in Indonesia to actually cope with these conditions, because it's an incredibly challenging environment, but one that I certainly won't forget. It was extremely memorable, and I hope to go back one day. So it was a good experience all round. And that's me finished really. So I've kind of covered my slides. I don't know whether you want to do joint questions with myself and David at the end, but certainly that's my my experience on the pipelines of the Palu region and how I supported the ADB and the designers with the design and construction of those pipelines. So I appreciate your time. Oh, I've got a question from Phil.
Hi, Glyn. Can you hear me okay?
I can hear you, Phil. Yeah.
Yeah, thank you very much for the presentation. Absolutely excellent. Some great great methods that are employed for difficult conditions like this. I'm a geotechnical engineer and I work here, so I'm yeah, very familiar with some of these problems. Just on managing risk, when you rebuild after the earthquake, who makes the decision as to how secure it will be in regards to another earthquake? And who takes the risk if it fails again? How did you handle all that?
Yeah, that's a great question and probably the most challenging bit. So first of all, I didn't know we had a geotech engineer on the call. I would have been a lot more nervous. I'd known that from the start. So
Well, Mike's on the call as well, so he might have a question.
So yeah, I approach this very much from the point of view of minimizing risk and actually balancing cost against risk. That the contractor had obviously bid to build this pipeline and had a budget in mind, and I was then coming along and trying to rock the boat, if you like. So the ADB were incredibly supportive of me, and I was surprised at actually how proactive the ADB were, and certainly the technical support they gave to make sure that obviously the money was being spent the best possible way. So they were very much looking for me to give them assurance that as everything that could be done was being done. But in terms of the ultimate responsibility, yes, I still to this day don't really know where that lied. Certainly the designer didn't particularly take much responsibility for it. They, as far as concerned, were just building to a plan. The constructor, as you're aware, just wanted to get the pipeline in as quickly as possible. So the government itself, I know, came and inspected and wrote my report, and they were the ones that probably gave it most attention. But certainly there was no obvious lead on that in terms of who would take liability if it failed again. It was almost like, well, we've done the best we can, and that's all we can satisfy ourselves with. Now, the leak detection system I mentioned, it's actually our system that I put in, so I'm slightly biased on this. But we give minimum guarantees of leak size and leak location and leak accuracy that we will find if there's a leak. So we would be liable if we missed the leak or didn't spot it. But ultimately, in terms of the accepting the pipe, look into whether to accept whether the pipe should have failed if there's another earthquake. Yeah, I don't know, and that's the area where I felt that there was no real ownership is probably the best word I would give, which is, I guess, a very British word for it. But there was no ownership for the ultimate design. I felt that it was nobody took responsibility, which I'm used to working in places like Indonesia with that, but it's incredibly challenging because who would take responsibility? Because the earthquake was so devastating in 2018 that I don't know really of any pipeline that could survive that, even if you had a huge budget. The liquefaction was that bad. So I think it's just accepted that nature would win is probably the answer. A simple answer.
Yeah, no, your answer is fine, and the approach is obviously very practical. The problem is that when we're designing, and the more we understand about earthquakes and do probabilistic seismic hazard assessments, of course, the accelerations go up, and we're reaching a point in some projects where we're just getting really lost in terms of what we designed for, because the seismic risk in Indonesia is massive, and it's getting, on paper, it's increasing because we learn more about it, and I'm sure that they had similar problems in Japan and New Zealand. Your approach and what you did is practical and what we would like to do, but it's it is causing problems in other fields. Anyway, thank you for your answer and your presentation.
Yeah, I know it's my pleasure. Yeah, just to add to that, I mean, as part of the work I did, helping to write the guidelines for protecting earthquake pipelines for earthquake regions in Indonesia, I read literally dozens and dozens of papers and articles from all over the world, and none of them were relevant to Indonesia because they just did not cover the question. They just didn't. It was just every country has its own problems and challenges, and you know, I mean, certainly, for example, in New Zealand, it very much seems to be, you know, survivability, getting the system back up and running as quick as you can. So that was the closest I had to Indonesia in terms of accepting it's probably going to fail, but making sure that you do all you can to get the system up and running as quickly as possible. But yeah, I agree. It's a real challenge. Yeah, I was surprised to see how unique Indonesia was when I started to look at the issues faced in Palu.
Yeah, thanks, Glyn.
Right, so we've got one question submitted online, and this perhaps goes back to your previous talk, Glyn. This is from Risky Sahil Pramono. What are the negative impacts of transmission hammers on piping systems? It seems a rather open question, but maybe you can give a quick answer.
Yeah, absolutely. Now that's my speciality, what I've done for 30 years. So yeah, the negative impacts are risk of failure. So certainly pressure transients can cause failures. Most of the work that we do in pressure transients, certainly in metallic pipelines, is the fact that actually it's not always a high pressure that causes the pipe to fail. So most pressure transients that cause failures aren't due to the pressure in the pipeline exceeding the rating and the pipeline ripping open. So if a pipeline, you ever see a pipeline that tears along its longitudinal axis, that's a high pressure causing it to fail. Most of them are due to the pressure wave, so the sudden hammer traveling on the pipeline. And as that travels on the pipeline at the speed of sound, which is about 1,000 meters per second in a metal pipe, it tries to move the pipe. And what it does then is it'll usually fail at joints, at bends, at thrust blocks. So it's not just about making sure your pressures aren't too high, it's making sure that you don't cause sudden changes in pressure, because a very short, sharp shock can cause a failure more so than a very gradual rise in pressure. So if you imagine you have a pipeline and you pressurize it very slowly, it's unlikely to burst unless you do pressurize it to a very high level. But actually, you can actually just change the pressure by 1 or 2 bars in a pipeline, and if you do it in a fraction of a second, it will cause the pipe to fail. So yeah, it's a very open time. I'm happy to answer more questions on that and in the future another time. But yeah, it's a very good question, and the answer is it's more the rate of pressure change that causes the failure, not the actual magnitude of the pressure itself.
Okay, thank you. I'll just check. We have a question here at the EP for you.
Good evening, Glyn. How are you?
I'm very good, thank you. Nice to meet you.
All right. I'm Robbie from TDW. Just one quick question. You mentioned about pipes, about HDPE and GIP, which is galvanized iron pipe. And I just quick question, why is not using let's say a black steel and then you coat it with a let's say a coating or without a rust preventer, and then also for the pressure, usually for transmitting water from along, let's say 10 kilometers, and that, let's say 10 kilometers, usually using a pressure lead. How many pressure relief valve that is suffice to transfer that water into that place? Thank you.
Okay, thanks for your questions, Robbie. So yeah, 2 good questions. So first of all, the answer, yeah, the steel pipe would be a very suitable pipe. We were very much governed by cost on this project, and the truth is, galvanized iron pipe is manufactured mainly in Indonesia, so it's readily available. It's relatively cheap, and again with HDPE, a lot of it is manufactured in Indonesia. So it was the cost of the pipe material that was the governing factor. Now, I know they also make steel pipes in Indonesia, but steel pipe is a lot more expensive. So the answer was we were trying to minimize costs. And at the time I got involved, most of the tenders had already been awarded and would be costed on galvanized iron. So HDPE is of a similar cost to galvanized iron, so it didn't affect project budgets too much. But if I'd started from the scratch and I had a high budget, I would have used steel pipe instead of galvanized iron, or I would have used ductile iron because they're more resilient. So it was just on availability of pipe and cost of pipe because it's manufactured locally. In terms of the pressure relief question, that's an interesting point. So generally on a pipeline, if you needed a pressure relief valve, now generally you'd only put a pressure relief valve on a pipeline if you were going to close a valve quickly or suddenly. And normally we would say, wherever you have a valve that you could close against flow, you may well need a pressure relief valve at that location. And you would carry out a surge analysis study to size it and verify it. For most water pipelines, you probably wouldn't. You would just look at what would happen when the pump stopped and started, and they're the main causes of pressure transient. And if you had a pressure transient issue due to a pump operating, you could either put in some sort of surge vessel to protect the pipeline, which is an accumulator or pressurized air vessel to reduce the severity of the pressure changes, or you would look to other measures such as having variable speed drives that you could run the pumps down with potentially some sort of battery to allow you to do that if you lost power. So each system's treated in its own. For water pipelines, pressure relief valves are not that common. For oil and gas pipelines, they are very common because you need emergency shutdown procedures and you need to be able to close valves very quickly. So going back, my answer will be if you can close a valve against flow quickly, you should probably put some sort of pressure relief valve at that location. The challenge you have for oil and gas pipelines is you can't just release that product through the pressure relief valve into the environment. So for water, you can open the valve and it can just run away because it's water. But for petrochemical pipelines, you need then some sort of way to contain the lost product through the relief valve, which again then increases costs. So each project you would treat in individually and look at the needs primarily. And if you can design out a pressure relief valve, it's worth doing so.
Okay, thank you, Glyn. We've got one more question submitted online, and I think we'll have to then move on to our next speaker. But this question actually explains why there's a familiar voice missing this evening. This is from Mike Doby. It says, "Great presentation. I've lost my voice. But I think the very difficult thing is applying the lessons learned to other locations and situations. How many more Palus are there?"
Yeah, that's a great question. I appreciate that, and that's why the ADB were keen to have national guidelines. But ultimately, yes, if the earthquakes never happened, then maybe people don't realise it could happen, and that's certainly something that I concur with. Yeah, I mean these all great questions. It's that monitoring and who has responsibility for making sure that the pipeline routes have been checked for seismic risk, to make sure that the pipeline has been designed to accommodate that. But I would imagine there will be many more Palos, even with existing infrastructure. It's always a risk. So all you can do then is react and build back better, which is what they tried to do. But when I was helping to write those guidelines, I thought exactly the same thing. I mean, Indonesia is vast, and there will almost certainly, unfortunately, be more poor Palos at some point.
Thank you very much, Glyn, and thank you for your comprehensive answers and your presentation. We'll move straight on now to our third speaker of the evening, David Meigh.
Is there a pointer I can use? Yeah, that's the start. Yeah. Yeah, that's the correct one. It doesn't matter. It's okay, it doesn't matter. Oh, hello, it's me again. I'm going to talk about first of all, about the repair to the irrigation project. I put this photograph because it quite clearly shows the repair of the irrigation, and behind it, the new pipeline going in. So it's the best of both worlds. A bit slow. Yeah, okay. So actually, the presentation, I've reminded you of the event and the damage to the irrigation works. Then the Gumbasa irrigation scheme, problems I encountered at the headworks, liquefaction along the main canal and structures, secondary and tertiary canal repair, soils in a pilot area, and then the SCADA system for real-time water management. And then a few slides on improving the water supply headworks, and a slide on the fishermen's harbours. When I got there, the problem wasn't earthquakes. The problem was floods, and they were having quite a serious flood. This doesn't seem to be moving. Anyway, you can see on the left-hand side, this is the flood bank, and the river has breached it upstream and is now attacking the road on the left. First of all, you can see that this was new bank protection here that was also damaged. And this should be a video, but it just seems to be stopping and starting. You can see just at the corner by the bridge, the road has disappeared. And the area just behind the road, this green area, is actually a lot lower than the river. So they were very fortunate that the whole river didn't change course and bypass the weir. Just if you look at the bottom left-hand corner, you can see the pipeline exposed, the existing pipeline exposed and damaged. And the weir, which is here, is completely covered by sediment and gravel and boulders. Here on the bottom, well, it was on the bottom, on the right-hand side, the flood bank downstream was damaged. And we've already moved on to onto the photographs. But this is my photographs of the road when I got there. And you can see this part of the road on the right-hand side is almost completely gone. So they had to build a second road around it while they repaired it. On the other photograph, you can see, well, on both photographs, you can see the existing pipeline completely exposed and damaged. Downstream, you can see here on the left was a masonry wall, completely undermined and eroded. Once it was made of masonry, and once you expose masonry, it just crumbles, and it continues to crumble in a progressive failure. and this is what's happened here. And further downstream, where the what's called the flushing channel emerges, the wall is also removed. So a lot of flood damage. That just downstream of here, you can see the old river channel, but the river has now taken a new channel. It's turned right because of the flooding, and rivers like to move across their floodplain if they're not prevented. So first of all, I had to deal with the flooding problems. The contractor was working on the weir, and he told me that 8 times he'd built a cofferdam to repair the weir, but 8 times it had been washed away. Well, if you build something from rounded river boulders that move during a flood, you could expect it to get washed away. And it seems that 8 times he'd learned nothing and not come up with an alternative design, which I provided, but because I had such a short visit, I don't know if they implemented. But you can see that their design proposed on the left-hand side shows a masonry footing and an inclined wall. But as soon as the river starts cutting that, it will just fragment. So I proposed a reinforced concrete wall with a sound base and in 30-meter lengths, which takes a lot more removing by the river. So a lot more stable. And once again, I don't know if they went after I left, whether they adopted this this design. This shows what happened to the main canal. There was huge soil heave, completely threw up everything that was on the main canal and damaged all the structures. Any lining like this was completely damaged. So very, very violent earthquake and a very serious damage along the whole canal. So this shows you the repair of the canal, which is going to have a polyethylene lining to prevent leakage, because it was leakage from the canal that might have caused much of the liquefaction, because the canal is sitting sometimes 10 meters, sometimes 5 meters above the land to be irrigated. And seepage from the canal seems to have also contributed to failure. And then there's an in situ base and panels on the sides. This section had been completed the day before, and there wasn't a lot of evidence of concrete curing. So I made that point to them, and within the afternoon, it was already covered by tarpaulins being soaked with water. Oh, I don't know what's happened here. This is the Sibilaya washout, which is just about 4 kilometers down the main canal, where there was a breach, and you can see that there was a liquefaction and a breach, and you can see how it spread over the rice field, doing a lot of damage. You can see the rice fields above. That's what was here previously. I'll come back to that a bit later. We're very aware now of trying to replace concrete or masonry, if possible, by nature-based solutions. And one of the most effective is a grass called vetiver that has roots that can go down to 6 or 7 meters, which is incredible, and they're incredibly strong. So the idea here to support the canal in this failure area was to put layers of geogrid horizontally, and the vetiver roots would come down vertically. Now the geogrid has holes in it, so you expect the roots to go through the holes. Somehow this message didn't get to the consultant geotechnical engineer, who changed my design from geogrid to geotextile. And by the time I got there, there was 20,000 meters of a geotextile filter with no holes in it. So, you know, these things do happen, don't they, in Indonesia? So rather disappointing that my trial design was not completed. So as I said, I propose using better geogrid hybrid, but the National Geotechnical Specialist had other ideas. And this was after I'd agreed the drawings. This shows what's called a cross regulator on the main canal. It controls the water level. They previously been built in masonry and been completely fractured. I pressured them to try and design everything in reinforced concrete because it has so much more strength in tension, and hopefully it will withstand earthquakes better. I was a bit critical of, you can see on the left-hand side, I said to them, how on earth are you going to compact the soil there? It looks, you know, and the answer is that they're not. They're just going to throw the soil in, and hopefully the wall will survive. Coming. Is it going to come up? I suggested that they actually built the embankment first to the right lines and levels and compacted it very vigorously, so that we had a really good foundation before they even put they put the reinforcements, and then they put in a lantai kerja, either plastering or in panels, the precast panels, and then they put in the steel, and as they concreted, they moved the outer planks up so that they get good compaction. So there was something like 51 of these structures on the main canal. So you can see it was quite a big job. Some of them were still intact and they were just repaired, but many were damaged and had to be completely replaced. So this was another example of the two departments not talking to them, even though it's the same Department of Public Works. The water supply had put the pipeline here, and they put a pedestal. This actually is a river coming through. And if you look at the other photograph, this is what's called an overshoot. This is actually filled with sediment, which they had to clear. But the river is supposed to come through here and over the canal. But if you put a pipeline in the way, it may not last that well, particularly if it's got a pedestal that's going to be undermined by rapidly flowing water, because this is on a 5 to 10% slope. So the water coming through here in a flood would have a high velocity and probably take out that pedestal and maybe take out the pipeline. This shows you what happens when you build the canal. These are the secondary canals that are going down the slope, so they have water in quite high velocity. But you can see what happened. It's completely shattered. And on the other photograph, this canal is it's been completely displaced by almost half a meter. Shows you how violent the earthquake and the shaking was. We followed a design I used in Aceh after the tsunami and earthquake there, where you have what's this is concrete with mesh. A lot cheaper than reinforcement by putting mesh in, and there were supposed to be joints every 4 meters or so. So if there's an earthquake and it moves, you can actually lift the parts back because they should be intact. But this had the same problem as that structure, and you can see on the right hand side, I used the geotechnical test called the foot stamping test, and you can see that when I stamp with my foot, the backfill dropped about 20 centimeters. So clearly this solution didn't work either, and they should have a lot. This was cut through a lot of original soil, so they could have shaped it and then put a lining before they did the reinforcement. But you know, sorry if I sound like a critical person, but that's my job. The other problem on the project is soils and irrigation. Many of the soils are very permeable, and depending on the permeability of the soil, you have to choose what crops to grow. When I worked on the project in 1978, a long time ago. Probably you all weren't born then. And at the time, I worked with a agricultural soil surveyor called Carl, who may actually be listening in. I hope he is. Anyway, he divided the soils into 5 groups, A, B, C1, C2, and D, and described them as very heavy, meaning clay, very heavy clays, and then medium, shallow heavy to medium or light, and then light. Light in this sense means very sandy, no clay, and very liable to liquefaction. You can see the percolation rate for the A and B is 3.1 and A and B 3.1 or 3.5 millimeters a day, which makes them excellent rice soils. Great, go and grow rice there. And you can see below my recommendations in A and B: grow 2 crops of rice, then let it dry out a bit before you grow an irrigated palawija, so that the farmers can get 3 crops a year. In C, which is a percolation rate of 8 millimeters a day average, then just grow the rice in the wet season when there's plenty of rainfall, followed by 2 crops of palawija. So maize or soya, really good because it's a pulse, or beans or something. And then the really coarse soils, D, you can see they have a percolation of 61.2 average, 61.2 millimeters a day of percolation, which means that the farmers are filling them up all day and wasting so much water and saturating the ground. And this is the reason why it liquefied. And yet when this soil investigation was done, our soils advisor said this shouldn't be used for rice. It should be used for tree crops. And so I recommend that they start growing fruit trees there, because the roots are deep, hold the soil, and you only intermittently irrigate them with about a fifth of the amount of water you use for rice. So you keep the water table much lower, and the trees help to keep the water table low as well. So, and then and then the actual bank of the bank of the canal and the areas that are already liquefied, they should provide slope protection using vetiver and bamboo to try and help hold the soil. And so coming on from this, I proposed a pilot area with an extended area. The yellow lines are the pipelines, and coming from the main canal is so much higher than that you don't need to pump. You can get enough pressure in the pipes from gravity. So a very cheap solution. And at the time, Dinas Pertanian were covering the area in topsoil. So it was going to be a very productive area. And so I went out there with Dinas Pertanian and PU, the water resources people, and got them to try and agree to have a pilot area here. And I thought it was all agreed. When it went back to Jakarta, the guys in Jakarta said, oh, we can't do that, too difficult. So that wasn't done, and I went home feeling rather disappointed. But about a year later, I was contacted after my contract had run out, but never mind. I was contacted by the contractor and the RE and asked to help design a pilot area, but it in a different place. So this is what we came up with a den plot farm and a pilot area with high pressure laterals here, and then an extension area. The pilot area is here and down here, and hopefully the farmers there are going to grow fruit trees. Palu is not so far away from China, where I believe durian has taken off like anything. The Chinese in China love durian, but they can't grow it themselves. So that would be a great thing, dwarf durian, where you can pick the fruit, without having to climb the tree, would be a really good option. And then the other thing that they wanted, just like the pipeline, we wanted to manage the project in real time, so that we would put at all the main structures, we would put water sensors upstream and downstream, and we would have electric gates with actuators that would also send messages back to a control center. So the control center is at the headworks here on the left. And everywhere there's a cross regulator with a secondary canal, we can measure flows upstream and downstream, and we can measure flows into the canal. Now, the important thing in water management is the standard of performance between the client and the farmers. They are the clients, the irrigation department is the supplier. So that boundary is very important, but there are so many tertiary areas that are managed by water user associations. So here we suggested that the gurus, the water masters, they have smartphones, and when they go to each outlet, they measure physically, and then they send it by smartphone to the control center. And then once a day, if you have a color-coded schematic, you can see exactly which areas are getting enough water and exactly which areas are not getting enough. And you can rebalance the whole thing by operating the gates. First, we're going to operate the gates manually because there are gate operators. We don't want them to lose their jobs. And they also provide security for the equipment. So that was important. So that we designed a system for the whole scheme. But I suggested that we did the first 3 kilometers first and got it working really well, and then expanded so that we learnt our lessons and it would run much smoother. So hopefully that's gone ahead. Let me just say if that doesn't disappear. It is. Okay, assistance with the pipeline intakes. This is one of the pipeline schemes called DAU. And we wanted to see if we could make it quite cheap. And there was an existing sediment control structure here. So what we built was what is called a Tyroler weir, which is just after one of the drops. We put a grating. This, you can see a rack here, and the water will drop into the rack. If there's a flood, the sediment tends to leap over the rack, and just the water goes in. And then that's taken in a channel, and you can see this is actually a satellite image of it constructed, so that you can see the rack down here, and then there's a channel that goes into a sediment basin. I've sort of misspelled that. I'm sorry. That's the sediment basin here, where any sediment drops out, and then the water goes into the pipeline. And then whenever the sediment basin is full, you close the pipeline gate and you open the flushing gate, and within half an hour, it should flush all the sediment back into the river. So, and then hopefully you get much cleaner water. I just put in another photograph because it's such a nice last slide. And then this is the Pasigara. Oh, it's not come up yet. This is the Pasigara intake. This is the pipeline that Glyn was mainly talking about, and it was my job to look at the design. And you can see the intake. The intake is at right angles, which means that the water has to turn through 90 degrees. This is a very flashy, very heavily sedimented river. And a lot of the sediment will be caused by vortex to be whipped up and brought into the canal. And then they have this strange arrangement with a curved sediment basin. Well, the secondary canals generated in the curve would keep the sediments in motion. They're not a very good idea, although they proposed, they thought the fault line ran through the middle. The red line is a fault line that they thought ran through the middle. So not very good idea to build your structures in the middle of a fault. And then it went to the intake there and down to the treatment work. So intake it right, curved sediment base. Now this was my design, which had a much smoother intake, so that you didn't get as much sediment coming into the intake. And then you had what are called vortex tubes, which are tubes under the canal bed with an aperture, and it causes a vortex, which takes away the bed load, the fine gravels and sands, and it would flush those back into the river. And then the hopper bottom sediment basin is here, 2 channels, and it's in a hopper bottom shape to make it easy to flush, because you get more flushing power at the bottom of the channel. And so that would normally operate at a high level, but then when it was full of sediment, you would drop the level by opening the sluice gate and then sluice out the sediment, maybe once a month. And then across the fault, I proposed these neoprene flexible joints, very similar to what Glyn proposed on his pipeline. But the other thing was that this is a very flashy stream. And when there's a thunderstorm for about an hour, the river turned full of sediment for about 4 hours. So it was very heavily sedimented for 4 hours, but then it cleaned up and became clear. So my suggestion was that we we have a clear water poly tank with enough water to last for at least 4 hours before, so that we could close the intake when there was a flood. We had the water stored here, which goes into the system for 4 hours, and then hopefully the river will be clear again before we have to open the intake gates. So that was my idea there. And I'll just finish with my fishermen's harbours. I'm I'm not a coastal engineer, so I was asked to help design the fisherman's harbour. But you know, fortunately, I have an identical twin who is a coastal engineer who gave a presentation here about breakwaters, and he gave me advice. And the advice seemed to be that if you have a narrow gap, you create very, very large waves, which would seem to make it difficult for the fishermen to come into the harbour during a storm. And you got very big waves, quite exciting for them. And then on this second one, the fishermen were supposed to come near the coast, but you've got large waves pushing them this way, pushing them onto the beach when they have to try and turn a right angle. And on this side, you have the Palu River just emerging here. So you're probably allowing sediment to fill in this part. And the other problem was that there was a drain coming in here. The water was black. It was so highly polluted. And this is an area where fishermen are throwing fish into the bottom of their boats. There's dirty water in the bottom of the boats. So the fish are getting infected by the dirty water coming in at this almost like a sewer pipe. So that was a good idea. So our idea was to do a similar, do our breakwaters shaped like this, because that gives you a protected entrance where the waves are still. There's no problem with waves. Anyway, we gave this advice. Unfortunately, it wasn't followed. And this shows the model. So you can see the waves coming into the bay, but when they came through the entrance, you get these great big waves. And yet, even with the model, they wouldn't agree to change to our design. But never mind. And then above is the picture of the Fisherman Harbour. This is actually Fisherman's Harbour 2, and you can see the pipe coming in just on the right-hand side. So I think I've just about finished. Have I? Yeah, terima kasih. Thank you for listening.
Thank you very much, David, for your presentation on fishermen and irrigation. Very informative. Do we have any questions? We'll just have a couple of minutes for questions before we have dinner. We got any questions on David's presentation? Any online questions?
It was obviously perfectly understood.
I think my question would be, both in your original introduction and during this your presentation, you essentially said that the irrigation system contributed to the earthquake by lubricating the fault.
No. Lubricated the soil because the liquefaction, not the fault.
Liquefaction. Okay, sorry. But I just wondered, did anybody consider that perhaps this wasn't a good place to have an irrigation system because of that?
Well, actually, the alignments were already chosen when the project was designed in 1976. Although the company I worked for were involved in the design, but at that time, the earthquake factors were only a third of what they've been updated to now. So it wasn't considered a very high risk area at the time, which was a shame. And our soils specialist advised not to grow rice in those areas. He proposed other crops that would be dry land so that you wouldn't be soaking them with water all the time.
Yes, that sounds more sensible, doesn't it? No other questions? In that case,
No, there's one
sorry,
over
there's
here.
one here. Oh, okay. So you keep.
I'm Raka, I'm from Binus. I have a question regarding the potential environmental consequences that could arise from the design changes, particularly with regards of river flow patterns and the ecosystem around the reservoir.
Sorry, can you repeat that as well?
What are the potential environmental consequences that could arise from the proposed design changes, particularly with regards to the river flow patterns and the ecosystem of the nearby reservoir?
Yeah, well, the problem was that the farmers a lot of the farmers are from Java, and they're used to growing rice and only rice, and getting them to grow other crops is always difficult. And that was the reason why we wanted a pilot area to demonstrate that they could safely grow tree crops on these poor soils. Unfortunately, I was thwarted at the time by the area I chose for a pilot area was not accepted in Jakarta. But then something like, I don't know, 6 months or a year later, I was approached again to design another area for this pilot area. So I hope that's gone ahead. Thank you.
Right, I think we've run over time, and so we must draw to a close. Yes, and I'd like to hand back to Phil Woodmansey to make the closing remarks.
Thanks, Chris. And first of all, thank you to our speakers. It was really interesting to listen to everything that's going on in the field of seismic engineering. Glyn, particular thanks to you for joining us. I think you're in the UK, I think. Really appreciate you taking the time to talk to us and acknowledge how much you love working in Indonesia. I hope David doesn't find the work too frustrating. It's a tremendously challenging country to work in, and I certainly love working here, and I'm glad to hear that you do. And Samuel, thank you for coming along from Binus and showing us some of the sophisticated and analytical work that you're doing as well, because all this it really helps to contribute to building and understanding how our country behaves during the seismic events. It's really important that we keep up that that level of research. So I'm very conscious that, those in EP are trying to get to their dinner. We had about 80 people at least online, so that was fantastic, and I hope those online enjoyed the presentation as much as I did, and I hope you guys at EP have a good evening. And so from me, thank you very much, and thank you for joining our presentation, and we'll see you next time.
Thanks, everyone.